So here's the deal. Your data is a mess. No offense, but it's got noise, redundancy, and way too many dimensions. It's like trying to watch a 4K movie on dial-up internet. Just too much going on. But don't worry, because today we're talking about autoencoders, the unsung heroes of machine learning that know how to take that chaotic data, squeeze it into something smaller and more useful, and then magically reconstruct it. Think of them like the ultimate data Marie Kondo, keeping only what sparks joy and ditching the rest. Now, these things aren't just good at cleaning up data. They're also spies. Yeah, you heard me. Autoencoders are experts at secretly learning patterns, detecting anomalies, and even generating brand new content. Ever wonder how your banking app catches fraud before you even realize something's wrong? Or how AI removes noise from old photos like it's giving them a fresh coat of digital paint? That's right. Autoencoders are doing all the heavy lifting behind the scenes. So here's what's coming. First, we'll break down what autoencoders actually do and why they're like a really good compression algorithm, but with a PhD. Then, we'll look at the different types. Some just compress and reconstruct, while others get fancy with probabilities and denoising. And if you've ever been curious about how Netflix, medical imaging, or self-driving cars use them, you're in for a treat because their applications are straight up sci-fi level. Of course, it's not all smooth sailing. Autoencoders have their quirks. Sometimes they overfit, sometimes they struggle with imbalanced data, and sometimes they just refuse to learn anything useful, which honestly is pretty relatable. But we'll go through all the tricks to get the best results, compare them to other dimensionality reduction techniques like PCA, and even see how they play a role in natural language processing. And just when you think we've covered everything, we'll talk about the future, because autoencoders are evolving and their newer versions are even more powerful, helping AI systems generate images, detect cyber threats, and maybe even help AI understand human creativity. It's going to be fun, it's going to be nerdy, and by the end, you'll have a new favorite machine learning tool. Let's go. Autoencoders are like that one friend who can summarize an entire 3-hour movie in 2 minutes, but still keep all the important details. They take a bunch of complex data, squeeze it down into something smaller, and then reconstruct it back, hopefully without losing anything crucial. It's like stuffing a giant suitcase into a tiny backpack and then pulling everything out without a single wrinkle. Sounds like magic, right? Well, it's just really smart math. And here's the best part. They do all of this without supervision. No labeled data, no step-by-step instructions, just raw, unfiltered information. Imagine throwing a toddler into a room full of Lego bricks and expecting them to build a perfect replica of the Eiffel Tower. Sounds impossible, but give them enough time and maybe some frustration, and they'll start figuring out the patterns. That's exactly how autoencoders work. They learn by trial and error, refining their ability to compress and reconstruct data over time. Now, why does this matter? Because data in the real world is messy, bloated, and full of useless noise. Think about your email inbox. 99% of it is junk, but somewhere in there is an important message you actually need. Autoencoders do the same thing with data. They strip away the fluff and keep only what's essential. That makes them perfect for things like image compression, shrinking file sizes without losing quality, anomaly detection, spotting fraud before it happens, and even generative AI, creating completely new content from learned patterns. But here's the thing. Autoencoders aren't just some abstract concept used by AI nerds in lab coats. They're being used everywhere, from medical imaging to self-driving cars to recommendation systems. Ever wondered how Netflix figures out what obscure indie film you'd love, or how your bank catches fraudulent transactions before you even notice? Yeah, that's autoencoders quietly working in the background, making sense of all that chaotic data. Of course, this is just scratching the surface. By the time we're done, you'll know exactly how autoencoders work, when to use them, and how they compare to other dimensionality reduction techniques like PCA. And trust me, once you understand them, you'll start seeing them everywhere. buckle up, because this is about to get really interesting. Data is messy. Not just a few typos in an email messy, more like your entire garage after a year of stuffing things into it messy. The world is drowning in information, and most of it is clutter. That's where dimensionality reduction comes in. Imagine you've got a massive spreadsheet with thousands of columns, but only a handful of them actually matter. Would you rather analyze all of them or just focus on the important ones? Exactly. Dimensionality reduction is all about cutting out the fluff, keeping what's useful while tossing what's not. It makes machine learning models faster, smarter, and way more efficient. Now, you might be thinking, why not just delete random columns and call it a day? Well, it's not that simple. The goal isn't just to shrink the data, it's to do it without losing the important patterns. It's like summarizing a 500-page book into a single paragraph while still keeping the story intact. Cut too much and you miss the plot. Cut too little and it's still too long to be useful. Autoencoders are one of the best tools for dimensionality reduction because they don't just delete data, they learn what's important. They take high-dimensional data, compress it into a smaller representation, and then reconstruct it. If they can't rebuild the original input accurately, that means they cut out something important. So they try again, refining their compression skills until they get it right. It's like training a parrot to repeat a sentence. At first it's gibberish, but over time it starts making sense. And this isn't just useful for storage. Dimensionality reduction helps in everything from making deep learning models run faster to visualizing data in a way that actually makes sense. Ever try looking at a 100-dimensional data set? Yeah, it's impossible. Reducing it to 2 or 3 dimensions. Now, that's something you can work with. This is why dimensionality reduction is such a big deal in machine learning, whether it's for cleaning up noisy data, making algorithms more efficient, or just helping humans understand complex patterns. It's an absolute game changer. And autoencoders are one of the best ways to do it. Let's see how they pull it off. Autoencoders work like a high-tech shrink ray for data. They take a massive amount of information, squeeze it down into something compact, and then try to rebuild it without losing anything important. It's like taking a high-resolution image, compressing it into a tiny file, and then restoring it back to its full size, hopefully without it turning into a pixelated mess. There are 3 main parts that make this work: the encoder, the hidden layer, and the decoder. The encoder is the one doing the heavy lifting, taking all the raw data and figuring out what's actually important. It doesn't just throw away random bits, it learns what can be safely compressed while still keeping the core information intact. If you've ever packed a suitcase with just the essentials for a weekend trip, you get the idea. The hidden layer is where all that compressed information gets stored. Think of it as the AI's shorthand version of the original data, like when you take notes in class instead of writing down every single word the teacher says. If the encoding process is done right, this hidden layer holds everything needed to rebuild the original input later. The decoder is where things get interesting. It takes that compressed version and tries to reconstruct the original data as accurately as possible. If the autoencoder is trained well, the output should be almost identical to the input. If it's not, it means the model hasn't quite figured out how to balance compression with accuracy yet. It's like playing a game of telephone. If too much information gets lost along the way, the final message doesn't make any sense. When all 3 parts work together, autoencoders can uncover hidden patterns in data, filter out noise, and even generate entirely new content. It's not just about shrinking things down, it's about understanding the structure of the data itself. But to get there, an autoencoder needs training, and that's where things start to get really interesting. Training an autoencoder is like teaching an artist to paint from memory. At first, the results are rough. Details are missing, proportions are off, and the whole thing looks like a bad attempt at modern art. But with enough practice, the artist gets better at capturing the essence of the original image. Autoencoders learn the same way. They start with terrible reconstructions, but over time, they improve by minimizing the difference between their input and output. The first step in training is preparing the data. Just like you wouldn't bake a cake without measuring your ingredients, you can't train an autoencoder without normalizing and cleaning the data set. If the data is messy, full of outliers, or on wildly different scales, the model is going to struggle. The goal here is to make sure everything is in the best possible shape before feeding it into the network. Once the data is ready, it's time to build the autoencoder's architecture. This means deciding how many layers it should have, how many neurons go in each layer, and which activation functions to use. It's a bit like designing a house. You need the right structure to make sure everything fits together while still being functional. The encoder and decoder need to be balanced. If one is too complex and the other too simple, the whole thing falls apart. Then comes the actual training. The autoencoder takes an input, compresses it, and tries to reconstruct it. The difference between the original and reconstructed output is measured using a loss function, usually means squared error, MSE. If the reconstruction is bad, the model updates its weights through backpropagation and tries again. This happens over and over, adjusting tiny details each time until the autoencoder gets really good at compressing and reconstructing the data. Training isn't always smooth sailing. Sometimes the model overfits and memorizes the training data instead of learning general patterns. Other times it underfits and fails to learn anything useful at all. Tweaking the learning rate, adding dropout layers, or adjusting the number of neurons can help find the sweet spot where the autoencoder performs best. Once the training is done, the model is tested on new, unseen data to see how well it generalizes. If it can still reconstruct inputs accurately, it's ready to be used for real-world tasks like anomaly detection, image compression, or feature extraction. But if it struggles, well, it's back to fine-tuning and retraining. Training an autoencoder isn't just about making it work. It's about making it work efficiently and reliably. The encoder is the part of an autoencoder that does all the heavy lifting. Think of it as a really good summarizer. It takes a ton of data, figures out what's actually important, and throws away everything that isn't. If you've ever tried to pack for a trip with only a carry-on bag, you know the struggle. You can't take everything, so you have to decide what's essential and what you can live without. That's exactly what the encoder does, except instead of clothes, it's working with high-dimensional data. The way it works is simple. The encoder takes an input, processes it through a series of layers, and compresses it into a smaller representation. Each layer applies transformations that help highlight the most important features while ignoring redundant information. It's like filtering out background noise in a crowded room so you can focus on a single conversation. The goal is to create a compact version of the data that still holds all the key details. This compressed version isn't just some random smaller copy. It's called the latent space representation, and it's the most crucial part of the whole process. If the encoder does a bad job, the entire autoencoder falls apart because the decoder won't have enough useful information to reconstruct the original input. It's like trying to recreate a painting from memory. If you don't remember the right details, the final version is going to be a disaster. A good encoder is all about balance. If it compresses too much, important details are lost and the decoder won't be able to reconstruct the data properly. If it doesn't compress enough, then it defeats the whole purpose of dimensionality reduction. The trick is finding just the right level of compression where the model captures the essential features while still reducing the data's complexity. The encoder's ability to extract meaningful representations makes autoencoders incredibly useful. It's why they're used in everything from anomaly detection to data compression. Once the data has been encoded, it can be used for all sorts of things, even outside the autoencoder itself. Some models use the encoded data as a more efficient input for other machine learning algorithms, making them faster and more effective. But the encoder is only half of the equation. Once the data is compressed, the decoder has to take that compact representation and reconstruct the original input as accurately as possible. And that's where things get tricky. The decoder is where the real test begins. It takes the compressed, stripped down version of the data from the encoder and tries to rebuild the original input. If the encoder is like stuffing a full suitcase into a tiny backpack, then the decoder is the part where you unzip it and hope all your clothes aren't a wrinkled mess. A good decoder can take that compressed information and reconstruct something so close to the original that you'd barely notice the difference. A bad decoder? Well, that's how you end up with blurry images, missing details, and reconstructions that look like they were made by a malfunctioning AI. The decoder works by reversing the transformations applied by the encoder. If the encoder compressed the data down to a latent space with fewer dimensions, the decoder expands it back up, attempting to fill in any missing gaps. It's like unfolding a crumpled map. You're trying to smooth it out and recover all the details without losing anything in the process. The challenge is that once information is compressed, some details might be harder to recover. If the encoder was too aggressive in removing data, the decoder is basically left guessing. The success of the decoder is measured by the reconstruction error, how close the output is to the original input. The lower the error, the better the autoencoder is at learning efficient representations. But here's where it gets interesting. Sometimes the goal isn't to reconstruct the data perfectly. In cases like anomaly detection or denoising, a little bit of imperfection is actually useful. If the decoder struggles to reconstruct an input correctly, it might be a sign that something unusual is going on, like an anomaly in the data. Decoders also play a huge role in generative models like variational autoencoders, where they don't just reconstruct existing data, but actually create new data that looks like the original. It's like an artist learning to paint in a specific style. After enough training, they don't just copy, they create. That's why decoders are used in things like AI-generated images, text, and even deepfake videos. When the encoder and decoder work together properly, you get a system that can take complex data, shrink it down, and bring it back to life with remarkable accuracy. But of course, none of this would matter if autoencoders weren't actually useful. So let's take a look at where they're being used in the real world. Autoencoders might sound like a niche AI trick, but they're actually working behind the scenes in more places than you'd expect. They're the silent workhorses of machine learning, helping with everything from fraud detection to making your favorite movies load faster. If data is the Wild West, autoencoders are the expert scouts, mapping out patterns, filtering out noise, and making sure only the good stuff gets through. One of their biggest superpowers is anomaly detection. Banks use them to spot fraudulent transactions by training an autoencoder on normal customer behavior. If a transaction suddenly doesn't fit the usual pattern, say your credit card is being used to buy 10 jet skis in a country you've never visited, the model flags it as suspicious. It works because autoencoders are really good at learning what normal looks like, and anything outside of that normal gets reconstructed poorly, which raises a red flag. They're also rock stars in image compression. Ever noticed how streaming platforms like Netflix or YouTube can deliver high-quality videos without eating up all your data? That's because deep learning techniques, including autoencoders, are used to shrink massive video files while keeping the details intact. It's like squeezing a full-size pizza into a lunchbox and somehow still having all the toppings when you open it back up. Another area where autoencoders shine is denoising. Imagine you've got a photo that's covered in static or a voice recording with a ton of background noise. An autoencoder can learn to separate the signal from the mess by training on clean data and then figuring out how to reconstruct an image or sound without the unwanted noise. This is why they're used in medical imaging, helping doctors clean up blurry X-rays and MRI scans for better diagnosis. And let's not forget feature extraction. Some datasets are just too massive to process in their raw form, so autoencoders can learn the most important features and pass only those to another machine learning model. This speeds things up and improves performance because the second model doesn't have to waste time on useless details. It's like handing someone a neatly summarized version of a long, boring book instead of making them read the whole thing. Whether it's making digital content more efficient, spotting fraud before it happens, or enhancing the quality of images and sound, autoencoders are already all around us. But they're not the only dimensionality reduction game in town, and sometimes another method might be a better choice. So, how do they compare to PCA? Let's find out. Autoencoders are great at compressing data and extracting useful features, but they're not the only tool in the game. Enter principal component analysis, PCA, the classic old-school method of dimensionality reduction that's been around longer than deep learning itself. If autoencoders are like a neural network-based data sculptor, carefully learning what's important and discarding the rest, then PCA is more like a strict mathematician, using hard rules to reduce dimensions in the most efficient way possible. The main difference comes down to how they work. PCA is purely statistical. It takes a data set, finds the directions in which the data varies the most, and then projects everything onto those key dimensions. It's like looking at a complex 3D object and figuring out the best 2D angle to view it from so that you still get most of the important details. Simple, elegant, and incredibly effective. Autoencoders, on the other hand, are powered by neural networks, which means they can model non-linear relationships in data. That's a huge deal because most real-world data sets don't follow neat straight-line patterns. PCA is like flattening a crumpled piece of paper to get a 2D view. It works, but it loses depth. Autoencoders can learn complex transformations, preserving more of the data's true structure. Another big difference, PCA is deterministic, while autoencoders are learned models. If you run PCA multiple times on the same data set, you'll always get the same results. Autoencoders, however, depend on how they're trained, the choice of hyperparameters, and even a little bit of randomness. That means they require more fine-tuning, but can also adapt better to different types of data. So, which one should you use? If you need a quick, reliable, and interpretable way to reduce dimensions, PCA is a great choice. It's fast, easy to implement, and doesn't require much computing power. But if your data set has complex structures and relationships that a simple linear method can't capture, an autoencoder is the better tool. At the end of the day, it's not about which method is better, it's about which one is right for the job. If you're working with high dimensional image data, autoencoders will likely give you better results. If you are just cleaning up a structured data set for analysis, PCA might be all you need. Sometimes the best approach is even combining both, using PCA first to reduce dimensions quickly, then fine-tuning with an autoencoder to capture deeper patterns. Autoencoders may have the upper hand in power, but they also come with more complexity. And speaking of different types, not all autoencoders are created equal. Let's take a look at the different flavors of autoencoders and what makes each one unique. Autoencoders come in different flavors, each with its own special abilities. Some are great at cleaning up noisy data. Others are designed for generating completely new content, and some are just minimalists that do basic compression. It's like picking the right tool for the job. You wouldn't use a sledgehammer to hang a picture, and you wouldn't use a simple autoencoder when you need something more advanced. The most basic version is the vanilla autoencoder. This one does exactly what you'd expect. It takes an input, compresses it, and then reconstructs it. No fancy tricks, just a straightforward encoder-decoder setup. It's useful for dimensionality reduction and feature learning, but if you need more specialized tasks, you might want to look at its more powerful relatives. Then we have the sparse autoencoder, which takes minimalism to the next level. Instead of letting every neuron in the hidden layer do work, it forces most of them to stay quiet, only allowing a small number to activate. This makes it really good at feature selection. It learns to focus on the most important details while ignoring the rest. It's like highlighting only the key sentences in a textbook instead of underlining the entire page. Next up, the Denoising Autoencoder, which is exactly what it sounds like. Instead of just learning to reconstruct data, it learns to remove noise in the process. During training, we intentionally add noise to the input, forcing the autoencoder to learn how to clean it up. The result? A model that can take a blurry or corrupted image and reconstruct a cleaner, sharper version. This is incredibly useful in medical imaging, speech enhancement, and restoring old photographs. If you're feeling fancy, there's the variational autoencoder, VAE, which is where things start getting a little weird. Unlike the others, which focus on compression and reconstruction, VAEs learn probabilistic representations of data. That means they don't just reconstruct what they saw, they can generate new data that looks like the original. It's like training an AI on a bunch of cat pictures and then asking it to generate a completely new, never-before-seen cat. VAEs are huge in generative modeling, powering applications like AI-generated art, deepfake technology, and even drug discovery. Each of these autoencoders has its own strengths and weaknesses, and choosing the right one depends on the problem you're trying to solve. If you just need compression, a vanilla autoencoder might be enough. If you need cleaner data, go with a denoising autoencoder. If you're working with feature selection, sparse autoencoders will do the trick. And if you want to dive into generative AI, variational autoencoders are the way to go. No matter which one you use, autoencoders have some serious advantages. But before we get too excited, let's break down exactly what makes them so useful and what their limitations are. Autoencoders might not have superpowers, but they come pretty close when it comes to handling data. They can shrink massive data sets, clean up noise, detect anomalies, and even help generate new data. It's like having a personal AI assistant that knows exactly what's important and what can be thrown out. But like any tool, they come with both strengths and weaknesses. One of the biggest advantages is dimensionality reduction. When dealing with high-dimensional data, think images, medical scans, or even complex sensor readings, autoencoders can compress the data while keeping the most essential features. Unlike traditional methods like PCA, which only captures linear relationships, autoencoders can model complex nonlinear patterns, making them way more flexible. Then there's feature learning, which is where things get even more interesting. Instead of relying on humans to decide which features are important, autoencoders figure it out on their own. They automatically learn which aspects of the data matter the most, making them incredibly useful for pre-processing in machine learning tasks. It's like skipping the boring part of data analysis and letting AI do the hard work for you. Another major strength is data denoising. If you've ever taken a low-quality photo or struggled to hear someone on a bad phone connection, you know how frustrating noise can be. Denoising autoencoders are trained to recognize what's important in an image or sound and filter out the unwanted stuff. They're used in medical imaging, speech enhancement, and even restoring old, grainy videos. Autoencoders also play a key role in anomaly detection, which is crucial for cybersecurity, fraud prevention, and industrial maintenance. By training on normal data, an autoencoder learns to reconstruct expected patterns really well. But when it encounters something unusual, like a fraudulent transaction, a manufacturing defect, or a hacker trying to break into a system, it struggles to reconstruct it properly. That difference between normal and abnormal data is what makes it such a powerful tool for spotting problems before they escalate. But autoencoders aren't perfect. One of their biggest drawbacks is overfitting. If they memorize the training data instead of learning general patterns, they become useless on new, unseen data. They also require a lot of fine-tuning. Choosing the right number of layers, neurons, and activation functions isn't always straightforward. And because they're neural network-based, they need way more computational power than simpler methods like PCA. Despite these challenges, autoencoders have become an essential tool in AI and machine learning. Whether it's compressing massive data sets, cleaning up noisy images, or detecting fraud before it happens, they're already shaping the way data is handled in the real world. But training them isn't always easy, and that's where the real challenges begin. Training an autoencoder isn't all sunshine and perfect reconstructions. Things can go wrong in all sorts of frustrating ways. It's like trying to teach a toddler to draw a straight line. Sometimes they get close, but other times they scribble all over the page, and you're left wondering if they even understand what a straight line is. Autoencoders go through the same struggles, and if you don't train them properly, they can end up completely missing the point of the task. One of the biggest headaches is overfitting. If an autoencoder is too powerful, it starts memorizing the training data instead of actually learning meaningful patterns. This is like a student who memorizes the answers to a test instead of understanding the material. Sure, they pass the exam, but the moment you ask them something slightly different, they fall apart. An overfitted autoencoder reconstructs training data perfectly but fails miserably when given anything new. Regularization techniques like dropout, weight decay, and early stopping can help keep the model from turning into a glorified photocopier. Then there's training instability. Sometimes the loss function behaves like a roller coaster, jumping up and down unpredictably. This can happen if the learning rate is too high, causing the model to make wild updates instead of gradually improving. Other times it's too low, and the model learns at a painfully slow pace, taking forever to converge. Getting the learning rate just right is crucial, and techniques like adaptive learning rate adjustments can help smooth things out. Data imbalance is another sneaky problem. If the training data is mostly made up of one type of pattern, the autoencoder will assume that's the only thing that exists. This becomes a real issue in anomaly detection. If an autoencoder is only trained on normal cases, it might struggle to recognize subtle anomalies because it simply hasn't seen enough variation. One way to fix this is by using data augmentation or artificially generating more diverse samples to balance things out. Even when everything is working fine, bottleneck size can make or break an autoencoder's performance. If the hidden layer, latent space, is too large, the model stores too much information and doesn't actually learn to generalize. It just copies the input with no real compression. If it's too small, important details get lost and the reconstructions come out looking like blurry nonsense. Finding the sweet spot where the model captures just enough information without losing key details is a constant balancing act. Despite all these challenges, training an autoencoder is totally worth the effort. Once tuned properly, they become incredibly powerful tools for feature extraction, noise removal, and anomaly detection. But theory is one thing. How do they actually perform in real-world applications? One of the most impressive examples is image compression, where autoencoders can shrink massive image files while keeping the details intact. Let's see how that works. Storing and transmitting high-quality images takes up a ridiculous amount of space. If you've ever tried to email a high-resolution photo and got the dreaded file too large message, you know the struggle. This is where image compression comes in, and autoencoders do it better than most traditional methods. They're like a master chef who can take a full-course meal, condense it into a single bite, and somehow keep all the flavor. The process starts with data preparation. Before training an autoencoder, the images need to be cleaned, resized, and normalized. Feeding the model inconsistent data, like one image that's super bright and another that's dark and grainy, just confuses it. Standardizing everything ensures the autoencoder can focus on learning real patterns instead of getting distracted by unimportant differences. Next is the training phase, where the autoencoder learns to compress images into a smaller representation and then reconstruct them as accurately as possible. The encoder takes the high-dimensional pixel values and squashes them into a compact form, while the decoder attempts to rebuild the original image from this compressed version. If the reconstruction looks off, blurry, missing details, or just plain wrong, the model adjusts itself and tries again. This cycle continues until the autoencoder gets really good at finding the most efficient way to store the visual information. The real test comes with the encoding process. Once trained, the autoencoder can take any new image, compress it, and store it using way less space than the original file. The key difference between autoencoder-based compression and traditional methods like JPEG, autoencoders learn from data, meaning they can optimize compression specifically for the types of images they've been trained on. That's why they work so well for tasks like medical imaging, where traditional compression might lose important details, but an autoencoder knows which parts of the image are critical to keep. Finally, there's image reconstruction. When you want to view the compressed image, the decoder takes over, expanding the data back into its full-size version. A well-trained autoencoder can reconstruct an image so well that you'd barely notice the difference, even though the actual file size has been dramatically reduced. But if the model was trained poorly, the reconstructed image might look like something straight out of a bad dream. Blurry, pixelated, and missing key features. Autoencoders aren't just good at compression, they're also fantastic at spotting anomalies in images. If an input image contains something unexpected, like a defect in a manufacturing process or a medical scan showing an unusual pattern, the autoencoder will struggle to reconstruct it properly. That makes them perfect for quality control and automated inspections, but compression is just one of the many real-world applications of autoencoders. Another powerful use case? Anomaly detection, where they help spot fraud, security threats, and even early signs of disease. Let's take a closer look at how that works. Anomaly detection is where autoencoders really show off. They're like security guards who have memorized what normal looks like and instantly flag anything that seems out of place. Whether it's fraud in banking, faulty equipment in manufacturing, or even early signs of disease in medical scans, autoencoders can catch patterns that traditional methods might miss. The process starts with data preprocessing. Before an autoencoder can detect anomalies, it needs to be trained on clean, normal data. Think of it like teaching an AI what a perfectly cooked steak looks like. If you only show it good steaks, it'll immediately know when something is burnt or undercooked. In the same way, autoencoders learn the normal patterns in data, so when something doesn't fit, they struggle to reconstruct it properly. Once the dataset is ready, the next step is model training. The autoencoder learns to encode and decode normal data, getting better with each training cycle. If it successfully reconstructs an input with low reconstruction error, it means the data fits within the learned patterns, but if the error is high, meaning the autoencoder couldn't reconstruct it well, then something unusual is going on. That's the anomaly. Now comes anomaly evaluation. When the model is given new data, it tries to compress and reconstruct it. If the reconstruction error is below a certain threshold, the data is considered normal, but if the error is way off, the autoencoder flags it as an anomaly. The bigger the error, the more likely something strange is happening. This method works because anomalies, whether they're fraudulent transactions, cyber attacks, or manufacturing defects, tend to have patterns that differ from normal data, making them harder for the autoencoder to reproduce. This technique is incredibly useful in cybersecurity, where autoencoders can spot unusual network activity before a full-blown attack happens. It's also a game changer in healthcare, helping doctors detect early signs of diseases like cancer by identifying medical scans that don't fit the usual patterns. Even industries like finance and insurance rely on autoencoders to flag suspicious transactions, preventing fraud before it escalates. Anomaly detection with autoencoders isn't just about finding what's wrong, it's about doing it faster and more efficiently than humans ever could. Instead of manually combing through thousands of data points, AI can highlight the most suspicious cases in seconds, making real-world decision-making much easier. But anomalies aren't the only thing autoencoders are good at detecting. They can also clean up noisy data, restoring images and signals that seem completely lost. Let's dive into how they do that next. Data is messy. Whether it's a grainy security camera feed, a corrupted audio recording, or a blurry old photograph, noise is everywhere. The good news, autoencoders are fantastic at data denoising. They don't just reconstruct data, they learn how to filter out the junk while keeping the important details intact. It's like having noise-canceling headphones, but for data. The process starts by introducing noise types into the training data. This might be Gaussian noise, random grainy specks, salt and pepper noise, black and white dots scattered across an image, or speckle noise, distortions that make images look rough. Instead of just learning to reconstruct the original input, a denoising autoencoder is trained to remove this added noise, learning the difference between what should be there and what shouldn't. Once trained, the model becomes a noise removal expert. If given a corrupted input, like a smudged document scan or a voice recording with background chatter, the autoencoder can reconstruct a clearer version. It recognizes patterns in the data and learns to ignore the disruptions. It's like an AI-powered cleaning crew that knows how to remove stains without fading the fabric. This technique is widely used in image restoration, where AI cleans up old, damaged photos or removes compression artifacts from low-quality images. It's also essential in speech recognition systems, helping AI models understand human speech even when there's background noise like traffic or music. In medical imaging, denoising autoencoders help doctors get clearer X-rays and MRI scans by filtering out distortions that might hide crucial details. The beauty of autoencoders is that they don't need labeled data to do this. Instead of relying on human-annotated, clean versus noisy examples, they learn from raw data, making them more flexible than traditional filtering techniques. The more noise types they're trained on, the better they get at cleaning up different kinds of distortions. Denoising isn't just about making things look or sound better, it's about making data more usable. When AI can work with cleaner inputs, it leads to better predictions, smarter decisions, and more accurate machine learning models. Whether it's making your Zoom calls sound clearer, enhancing security footage, or improving voice assistants, autoencoders are quietly improving data quality behind the scenes. But they're not just cleaning up images and audio, they're also making huge strides in understanding text and language. Next up, let's explore how autoencoders are being used in natural language processing, NLP, to improve everything from sentiment analysis to AI-generated text. Text data is messy, complex, and often filled with redundancy. Autoencoders in natural language processing, NLP, are changing the way machines understand, generate, and compress text. They're like expert linguists who can summarize long paragraphs, clean up noisy sentences, and even generate completely new text that sounds human-like. If you've ever wondered how AI chatbots, search engines, or recommendation systems make sense of language, autoencoders are playing a big role behind the scenes. One of their biggest superpowers is data compression. Just like they reduce the size of images, autoencoders can shrink text-based data into more compact representations. This is useful in NLP tasks like topic modeling, where long documents are reduced to a small set of meaningful features. It's like taking a 500-page book and distilling it into a single-page summary while still capturing the essence of the content. Another powerful application is sentiment analysis. Instead of manually labeling words as positive or negative, an autoencoder can learn hidden patterns in text and encode emotions automatically. By compressing and reconstructing text, it figures out which words and phrases contribute the most to the overall meaning, making sentiment classification more accurate. This is how AI can detect sarcasm, anger, or excitement in customer reviews and social media posts. Autoencoders are also widely used in text generation. Variational autoencoders, VAEs in particular, can generate new sentences based on what they've learned from training data. This is huge for AI-generated content, from chatbots that mimic human speech to creative writing models that can produce poetry, essays, and even entire news articles. It's the same tech that powers AI writing assistants, helping to auto-complete sentences and generate realistic dialogue. Another game-changing application is machine translation. Autoencoders help translate languages by encoding text from one language into a universal latent space and then decoding it into another language. Instead of simply mapping words one-to-one, autoencoders learn deeper relationships between sentence structures, making translations more natural and contextually accurate. This is how AI-powered tools like Google Translate have improved beyond basic word substitution. Perhaps the most underrated use case is anomaly detection in text. Autoencoders can flag unusual writing patterns in legal documents, detect fake reviews, or even spot potential cybersecurity threats hidden in text-based logs. If a message doesn't fit the usual structure of human-written content, the autoencoder struggles to reconstruct it properly, raising a red flag for further investigation. Autoencoders are revolutionizing NLP by making language more machine-friendly, improving accuracy in AI-powered assistants, and enabling smarter search and recommendation systems. Whether it's summarizing, generating, translating, or detecting anomalies, these models are pushing the boundaries of what AI can do with text. But the evolution of autoencoders doesn't stop here. They're constantly improving, and newer architectures are making them even more powerful. Next up, let's explore what's coming next in the future of autoencoders. Autoencoders are evolving fast, and the future looks even more exciting. As AI continues to advance, these models are becoming more efficient, more powerful, and capable of things we wouldn't have imagined just a few years ago. From generating hyper-realistic media to transforming the way we detect fraud, the next generation of autoencoders is set to change the game in a big way. One of the biggest trends is the rise of variational autoencoders, VAEs, and generative AI. Traditional autoencoders were mostly used for compression and reconstruction, but VAEs take things a step further by learning a probabilistic representation of data. This allows them to generate completely new samples that resemble real-world data. That's why VAEs are being used to create everything from AI-generated art to deepfake videos to synthetic medical data for research. The future? More lifelike AI-generated media, better content creation tools, and AI-powered creativity at a whole new level. Another major breakthrough is in anomaly detection and cybersecurity. As cyber threats become more sophisticated, autoencoders are being trained to recognize the tiniest irregularities in network traffic and system logs. Instead of waiting for security breaches to happen, companies are now using AI-driven anomaly detection to predict and stop attacks before they occur. The next step? Autoencoders that can adapt in real time, continuously learning from new data and improving their ability to detect emerging threats. We're also seeing rapid improvements in medical and scientific applications. Autoencoders are already used in drug discovery, where they help predict molecular structures and find new potential medicines faster than traditional methods. In medical imaging, they're getting better at detecting diseases in X-rays and MRIs, even in cases where doctors might miss early warning signs. The future holds smarter, more AI-assisted diagnostics, with autoencoders helping to detect cancer, neurological disorders, and genetic abnormalities earlier and more accurately than ever before. One of the most exciting developments is in self-supervised learning. Right now, autoencoders still require a lot of fine-tuning and parameter adjustments to get the best performance, but researchers are working on more autonomous autoencoders that can train themselves with minimal human intervention. This means they'll be able to adapt to new types of data on the fly, making them far more flexible and powerful for real-world applications. And let's not forget about AI ethics and interpretability. One of the biggest challenges in deep learning is understanding why a model makes certain decisions. The future of autoencoders isn't just about making them more powerful, it's about making them more transparent. Expect to see better explainability tools that help humans understand how these models work and why they make specific predictions, making AI more trustworthy and accountable. Autoencoders have already come a long way, but the next phase is going to be even bigger. We're looking at a future where these models don't just compress and reconstruct data, they generate, predict, detect, and adapt in ways we've only started to explore. To wrap things up, let's take a final look at everything we've covered and why autoencoders are one of the most important tools in modern AI. Autoencoders might have started as simple neural networks for compression, but they've grown into one of the most versatile tools in AI. From reducing data dimensions to detecting fraud, from generating realistic images to cleaning up noisy data, they've quietly become a foundational part of modern machine learning. Looking back, we've covered a lot. We started with what autoencoders are and why they matter. We explored their components, from the encoder that compresses data to the decoder that reconstructs it. We saw how they shine in applications like anomaly detection, image compression, denoising, and even natural language processing. We compared them to PCA, broke down their different types, and discussed the challenges that come with training them. And finally, we looked ahead at the future, where autoencoders are evolving into even more powerful, adaptable, and creative AI models. So what does all of this mean? It means that autoencoders aren't just a cool machine learning trick. They're a core AI technology that's shaping industries across the board. Whether it's helping doctors detect diseases earlier, improving security against cyber threats, or powering AI-generated content, these models are already transforming the way we process and understand data. But the best part? We're still only scratching the surface. AI is advancing faster than ever, and autoencoders will continue to evolve, unlocking new possibilities in self-supervised learning, real-time anomaly detection, generative AI, and beyond. So if you've been following along, congratulations. You now have a solid grasp of one of the most important machine learning tools out there. Whether you're looking to apply them in your own projects or just wanted to understand how they work, you're now ahead of the curve, and if you're excited about what's coming next, keep exploring. The AI revolution is just getting started, and autoencoders are going to be a big part of it.